Previously, we have characterized the tangent space to a submanifold by exploring two viewpoints of tangent vectors. We have either viewed tangent vectors as equivalent classes of curves, or we have looked at them in terms of coordinate. Now in this video, we're gonna give a final characterization of submanifold by exploring the viewpoint of tangent vectors as derivations on germs of functions. To understand this characterization, let us first review what this map is if we're viewing tangent vectors as derivations. Let's take a vector v in this tangent space so that it's a derivation on the germs of smooth function here. We want to define its image. Its image should be a derivation, but now on the germs of smooth function on the at fp. So if you're given germs of smooth function h here, right, at fp, we want to define the image of h. And a natural choice would be to take v of the pullback of h, because this composition then becomes a germ of smooth function at p. Now let me denote this just by f lower star. Then we can write this whole description more concisely as follows. So we have the following pairing. For every h that is a germ of smooth function at fp, the value of this on h is just going to be equal to the value of v on the pullback of h. So we have an adjoint kind of relationship here between the push forward of vectors and pullback of functions. Now observe that if h, this function h, vanishes on the neighborhood of fp, right, then this is just 0 in the germ, so this whole expression is 0. So then we have that this would be 0. This means that any vector, tangent vector of m that is a push forward of some tangent vector here must vanish on such h. It turns out that this is an if and only if, that if we have a tangent vector in m vanishing on such h, then it must be the push forward of some tangent vector v in n, if the manifold is an embedded manifold. So this gives us the third characterization. So let's discuss that in more detail. Okay, so let's assume that n is an embedded submanifold of m, so we can view this map as the inclusion map. Then we want to characterize the image of this tangent space, right, inside the tangent space of m. In other words, we want to see which tangent vectors of m actually comes from a tangent vector here. Which tangent vectors of m is actually the push forward of a tangent vector here. And the claim is the image of this tangent space is going to consist of tangent vectors of m that vanishes on the following ideal. So let me describe. So I will define I of n to be the set of smooth functions in m, the smooth functions on m that vanishes on this image. So this consists of all smooth function h on m such that h vanishes on the image of n. And now I denote the set v to be the set of all the tangent vectors in m at ip that vanishes on this set in, vanishes on these h. Previously, we saw that the image of this map indeed must lie inside this space, right? We already have that the image must lie inside this space because if we have the push forward of any vector v, when we pair it with such an h, like in here, by definition of the pairing, this is just the same as v applied to the pullback of h, and this is 0 because h was supposed to vanish on I of n. So we know that this image already lies in here. What we need to show now is that the other reverse inclusion. So we want to show that the image contains this. In other words, let w be a tangent vector in here, such that w vanishes on all the smooth function h that vanishes on in. In other words, w vanish on this ideal in. Then we want to show that w is actually the push forward of some tangent vector in n. Now let's take some coordinate, local coordinate xi at p, and we will write w in terms of this local coordinate. Observe though that because n is a embedded submanifold, so it's a regular submanifold, we can actually choose this local coordinate so that n is cut out by the last m minus n coordinate. Then we can see that in that case, the tangent space to n at p when viewed as a subspace, as a tangent space to M at P, is just going to be the span of these first n tangent vectors of these spaces. So to show that these W lie inside TPM, we just need to show that the last m minus n coefficient of W is 0, so that W actually lie in this span. But remember, how do we get these, how can we find this coefficient? Well, the usual technique is to apply both sides of this to the dual element of this. So in particular, if we apply both sides to xi, we'll just get wi. So this is equal to w of xi. Now, is w of xi equals to 0? Does xi satisfy our hypothesis here? Well, because on this coordinate neighborhood, this coefficient's at 0, so we do know that xi vanishes on this small open set, right? But not yet that it vanishes on the whole of n. But no problem, we can just fix that by, instead of using xi, we will just use a bump function. We take this bump function, where we require that it's 1 at P and it's near around P, and then it's supported in this coordinate neighborhood, and then we extend it by 0 all around n. So then, because this value of this pairing only matter on a small neighborhood of this anyway, these two values are the same. Okay, but this function now, it satisfies our hypothesis here. So this value is 0. And thus we have w of xi is 0, and that means that all of this coefficient wi is 0. So w indeed lie in the span of this partial x1 to partial xn, and thus it must be an image of the tangent space to n at P. So we can see that the tangent vectors of m coming from n are exactly those that vanishes on all the function vanishing on n. So that concludes our 3 descriptions of the tangent space of a submanifold. Next, we're going to look at some concrete example.